Welcome back. Today's goal of this lecture. Today I will see some question of singularity which had come different type of exam. Actually singularity, this topic is very important for any competitive exam, also for higher study. First example, at z equal to 0, the function fz equal to e to the power z plus 1 over e to the power z minus 1. Option 1, a removable singularity. Option 2, a pole. Option 3, an essential singularity. Option 4, the residue of fz is 2. Limit z tends to 0, e to the power z plus 1 over e to the power z minus 1. Notice z tends to 0, this value is 2 over 0 which tends to infinity. Since limit tends to infinity, that means the singularity is nothing but singularity is pole. So a pole, this is right option. That means removable singularity, essential singularity, these are wrong. And then the question about residue. Notice, at first consider a is z equal to e to the power z minus 1. And a is prime z equal to e to the power z. At z equal to 0, this value equal to 0 and this value is not equal to 0, because at z equal to 0, e to the power 0 equal to 1. And this is not equal to 0. So, this singularity, this pole is simple pole. And we all of us know, when singularity is simple pole, then the function fz over gz at limit z tends to 0, this residue is fz over g prime z. And this is equal to residue of fz at z equal to 0. This is equal to fz means e to the power z plus 1 and g prime z means e to the power z. And this value is e to the power 0 plus 1 over e to the power 0. This value is 1 plus 1 over 1. This value is 2. So, residue of fz is 2 at z equal to 0. So, option 2 and option 4 are right option. Sin pi z over 2 and sin divided by sin pi z. Then f has a poles. In which point f has a pole? This is the question. Option 1, all z. Option 2, all even integer. Option 3, all odd integer. And option 4, all integer of the from 4k plus 1. Consider this is fz and this is gz. Roots of sin pi z equal to 0, that means z equal to n at the point z equal to n. That means denominator are all integers and numerator are sin pi z over 2 equal to 0. This is equal to pi z over 2 equal to n pi would be cancelled, z equal to 2n, which represent all even integer. Even integer divided by even integer one over 1, then the singularity is removable singularity. and the numerator always even integer over odd integer. This is 0 and this is 1. So pole exists. We all of us know when the form is P over Q, then if order of multiplicity n of denominator and order of multiplicity m of the denominator, when n greater than m, then the singularity is removable singularity. When n less than m, then the singularity is pole. Here pole exists because the numerator always even integer and denominator is all integer. When the denominator is odd integer, then the pole exists. Option 3 is a right option. Another way we can solve same example is another way. Write sin pi z as, here sin pi z over 2 sin pi z over 2 times cos pi z over 2. This would be cancelled. That means this is 1 over 2 cos pi z over 2 and this is equal to 0, cos pi z over 2 equal to 0 when z equal to 2n plus 1. Here pi z over 2 equal to 2n plus 1 into pi by 2. Here pi by 2 would be cancelled, z equal to 2n plus 1 and 2n plus 1 is an odd integer. So for all in odd integer f has a poles. One shortcut rule for the rational complex function is, rules is for a complex function fz equal to pz over qz. If pz has zeros of order m and qz has zeros of order n, then z equal to 0, fz equal to pole when m less than equal to n and removable singularity when m greater than equal to n. When m greater than equal to n, m is the order of zeros of pole and n is the order of zeros of m is the order of zeros of pz and n is the order of zeros of qz. Then if m greater than equal to n, then if this order is greater than equal to n, then this singularity is removable singularity at z equal to 0. When z equal to infinity, then this would be reciprocal. Removable singularity if m less than equal to n and pole of order m minus n if m greater than n. Actually this would be the reciprocal. My next question, consider the function fz equal to sin z to the power m divided by 1 minus cos z to the power n, where z lies 0 less than z less than 1. When mn are positive integers, then z equal to 0 is 1. Removable singularity if m greater than equal to 2n, a pole if m less than 2n, a pole if m greater than equal to 2n. Option 4, an essential singularity for some values of m and n. First method, when m equal to 1, n equal to 1, then what is the limit? Limit z tends to 0. Since m and n I have considered 1, then fz equal to limit z tends to 0 sin z over 1 minus cos z, and this value is 0 by 0 from, so by L'Hospital rule limit z tends to 0 cos z over minus sin z, and this value tends to infinity at z tends to 0. So fz has poles when m equal to 1, and this is poles when m greater than equal to 2n. So option 3 is a right option. Next, consider m equal to 2 and n equal to 1. Sorry. This is wrong option. A pole when degree of m is less than degree of 2n. Since I have considered m equal to 1, that means 1 less than equal to 2. Then this has a pole. Sorry. Just look the method. Pole when m less than equal to n. Next, consider m equal to 2 and n equal to 1. Here m greater than n. We all of us know when m greater than n, then the singularity is removable singularity. Let's check. Limit z tends to 0, fz equal to sin square z over 1 minus cos z. This is also 0 by 0 form. Then apply L'Hospital rule. Limit z tends to 0, 2 sin z cos z. Cos z means minus sin z. Then this value is, here minus would be plus, sin z would be cancelled. Then this value would be 2. Limit z tends to 0, this value is 2. 2 is a finite number. So when m greater than equal to 2n, then this singularity is removable singularity. Next, I will see when m less than n. For this, consider m equal to 1, n equal to 2. Here also, since m less than n, that means the singularity is when m equal to 1 and n equal to 2, then this value would be sin z over 1 minus cos z whole square. This is also limit z tends to 0. This value is 0 by 0 form. Apply L'Hospital rule. Limit z tends to 0, cos z to 1 minus cos z and sin z. And at limit z tends to 0, this value tends to infinity. So the singularity here poles. When m less than 2n, this is pole, and when m greater than equal to 2n, this is removable singularity. Another method, we can solve it by zeros. Pz equal to here sin z to the power m and qz equal to 1 minus cos z to the power m. What is the order of zeros? Pz equal to, consider sin z. At z equal to 0, this value is equal to 0, and p prime z equal to cos z. At z equal to 0, this is not equal to 0. That means pz has 0 of order 1. But here sin z to the power m, that means pz has 0 of order m. Similarly, qz equal to 1 minus cos z. Sorry, here n, here n, 1 minus cos z. At z equal to 0, qz equal to 0, q prime z equal to sin z. At z equal to 0, this is also 0, q double prime z equal to cos z at z equal to 0, this value is 1. That means order of qz, order of qz is 2. But here qz is 1 minus cos z to the power n, that means 2n. Therefore, when m less than equal to n, then pole, and when m greater than equal to n, then removal singularity at z equal to 0. Here, order of 0 of at z equal to 0 of pz is m. When m and order of 0 of qz is 2n. When m less than equal to 2n, then pole, and when m greater than equal to 2n, then this is removable singularity. This is the another method, and this is the more easiest method than before method. I hope my all viewers have understood this question easily. Okay? Oh well. Next question, exp 1 over z plus I minus 1. Which of the following statement are true? Option 1, f has finitely many zeros. Option 2, f has a sequence of zeros that converges to a removable singularity. Option 3, f has a sequence of zeros that converges to a pole. Option 4, f has a sequence of zeros that converges to essential singularity of f. exp 1 over z plus I equal to 1, that imply e to the power 1 over z plus I equal to e to the power 2 pi ni. That imply 1 over z plus I equal to 2 pi ni. That imply z plus I equal to 1 over 2 pi ni. Z equal to 1 over 2 pi ni minus 1, and limit point of the zeros is minus 1, and limit point of zeros always converges to essential singularity. So, f has a finitely many zeros, this is wrong. Here n belongs to integer, infinitely many zeros. F has a sequence of 0 that converges to removable singularity, this is wrong. F has a sequence of 0 that converges to pole, this is also wrong. F has a sequence of zeros that converges to essential singularity, this is right. I hope my all viewers have understood. I have done one thing wrong. This would be minus I. Limit point of zeros is minus I. Next question, which of the following statements are true? Option 1, tangent is an entire function. Option 2, tangent is a meromorphic function on the complex plane. Meromorphic function means only singularity is pole. Option 3, tangent has an isolated singularity at z equal to infinity. Option 4, tangent has non-isolated singularity at z equal to infinity. Tangent means actually sin z over cos z, and cos z equal to 0 when z equal to 2n plus 1 into pi over 2. At this point, the function has a pole. So, since function has a pole, that means tangent is meromorphic function, and limit point of this pole is infinity. Since limit point of the pole is infinity and limit point of the pole always non-isolated singularity, so tan z has a non-isolated singularity at z equal to infinity. That means option 2 and option 4 has come. Option 2 and option 4 are true, and this question has come CSIR net 2018 June exam. Question, which had come CSIR net 2013 exam. The question is fz equal to z minus 1 exp means e to the power 2 pi I z minus 1. Then f has an isolated singularity at z equal to 0. Option 2, f has a removable singularity at z equal to 1. Option 3, f has infinitely many poles. And option 4, each pole of fz is of order 1. Fz equal to z minus 1 exp 2 pi I z minus 1. The pole are e to the power 2 pi I over z equal to 1. That means 2 pi I over z equal to 2 pi n I. And this is equal to, here 2 pi I would be cancelled. That means 1 over z equal to n. That imply z equal to 1 over n. At the point z equal to 1 over n, f has infinitely many poles. Where n belongs to integer. But when z equal to 1, notice here 0 e to the power 2 pi I means 1, 0 over 0. So apply limit L'Hospital rule, z tends to 1 over e to the power 2 pi I z over z minus 2 pi I over z square. And at the point z equal to 1, this value is e to the power 2 pi I means z equal to 1, e to the power 2 pi I means 1, this value is minus 1 over 2 pi I. This is finite value. So when n equal to z equal to 1, then the singularity is removable singularity. See option 1. Here z equal to 1 over n is the pole and limit point of the pole is 0. Limit point of pole is 0. And limit point of pole always non-isolated singularity. So f has an isolated singularity at z equal to 0. This is wrong option. This is the wrong non-isolated singularity. Now I will see each pole of order 1. Consider zz equal to exp 2 pi I over z minus 1. At the point z equal to 1 over n, this value is 2n pi I means 1. This value is equal to 0. And g prime z equal to actually e to the power 2 pi I over z minus 2 pi I over z square minus 2 pi I over z square. When z equal to 1 over n, then this value is 1 and this is minus 2n. This value is minus 2n pi I, which is not equal to 0. So each pole has order 1. That means option 2, option 3 and option 4 are right option. Fz equal to exp z over 1 minus cos z has a removable singularity, a pole, an essential singularity. Lorentz series expansion of fz around z equal to 0 is has infinitely many positive and negative part. Z over gz equal to, consider z equal to 1 minus cos z. Here given fz equal to exp z over 1 minus cos z, and this is 0 over 0 from. Then g prime z equal to 1 minus sin z, and limit z tends to 0, g prime z equal to 1 over sin z means 1 over 0, 1 over 0 equal to infinity. That means poles exist. And we all of us know, if gz has a pole, then e to the power gz always has an essential singularity. So option 3 is a right option. The Lorentz expansion of fz around z equal to 0 has infinitely many positive and negative part of z. This is also right. That means option 3 and option 4 are right option. Today I will stop here. In my next video I will see Roche's theorem. But at first I will hardly recommend you, please see today's video with pay attention. Actually this topic is very important for higher study, also for any competitive exam. Okay? See you soon, stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.